When you have projectiles, you're going to just shoot a cannon into the air. Its path of motion is going to look like that. But we remember from last unit that projectiles have both an x and y component. So this particular vector has an x component going that way and a y component going that way. This one's going to have an x component going that way and a y component going up. So again, this is you threw a ball in the air at whatever this happens degree is to the horizon. You're going to get an x component like that and a y component like this. For the last one, it's going down in the y direction. You still have a positive x and your y is just downward. All right, it says Nellie Newton tosses a ball along the dashed path. The velocity vector, complete with its horizontal and vertical components, is shown in position A. So what it's saying is this is my vertical component at A. This is my horizontal, or this is my Y, that's my X. Since there's no acceleration in the horizontal direction, right, on this T-chart, we know that for A of X, we put a 0. How does the component of velocity compare for positions A, B, and C? If you have 0 acceleration, is your velocity changing? Yes or no? No, because accelerations change in velocity. So if you have no acceleration, no change. So the x component at A is going to be the same at B and at C. They are the same. They are all equal. Because again, there's no acceleration. B asks, what is the value of the vertical component at velocity at position B? Remember when we did toss-ups? You toss something straight up in the air. At the very top of its path, what was its velocity just for a second? 0. So, in this trajectory of this thrown ball, point B is at the top. What is its vertical velocity?
0.
C asks, how does the vertical component of velocity at position C compare with position A? So, at A, it's going upward. At C, is it still going to be going upward? No, that ball's not going up. What's it doing? It's going down. Because points A and C are at equal height, I can say that they are equal and opposite. Any questions? Flip your paper over, please. There are three trig functions that we're going to be using. You know them. You learned them last year. I'll write the first one for you. So, what are the other two?
So, SOA, and then SIN. No,
SOHCAHTOA. That means the sine of theta is equal to the opposite over the hypotenuse. The cosine of theta is equal to the adjacent over the hypotenuse. And the tangent of theta is equal to the opposite over the adjacent. Gentle reminder, theta is the angle. So if you had something with vectors like this, we'd move those vectors around. So it look like that. Your resultant, or your hypotenuse, is there. And theta would be right there, which would make this one your opposite and that one your adjacent. So if you're given a resultant vector, which another word for that is hypotenuse, and an angle, you can solve for x and y components. To find the opposite leg of that triangle, my original equation is sine of theta equals opposite over hypotenuse. But I want to get opposite by itself because that's what I want to solve for. So to do that, I'm going to multiply both sides by the hypotenuse. those cancel out. So the hypotenuse times the sine of theta is going to be equal to my opposite. Which, in the majority of these, is going to be your y component. So to find my adjacent, my original equation is cosine of theta equals my adjacent over my hypotenuse. Do the same thing. I'm going to multiply both sides by the hypotenuse. These two cancel out. I'm left with the hypotenuse times the cosine of theta is equal to the adjacent, which in the majority of physics problems is going to be your x component. As a reminder, to find the hypotenuse, which we did last unit, a squared plus b squared equals c squared. C is equal to that hypotenuse or that resultant. And to find theta, theta is equal to the inverse tangent, opposite over adjacent, which is just me manipulating that toe apart of the SOHCAHTOA. So the projectile is fired into the air at a 35-degree angle to the horizon at 120 meters per second. Find the x and y components. First thing you do is you'd sketch out what you know. This would be my horizon. This is 35 degrees. And once you find x and y, I know that my x, go like that, and my y would be like that. Take a minute now to do that.
second code or was code?
My y vector is opposite of my angle, so I need to find my opposite. So I would use the hypotenuse times the sine of theta. In this case, my hypotenuse happens to be 120 times the sine of 35. And it should give me 69 meters per second with some rounding.
Wait, 120 times. What's SM?
S-I-N.
SM. So you plug the angle in there.
So 120 times the cosine of 35 should give you somewhere around 98 meters per second. Again, there's some rounding. To check it, a squared plus b squared equals c squared. Hopefully, 69 squared plus 98 squared equals 120 squared. We're going to talk about this actually because... Oh. So when I do 69 squared plus 98 squared, I get 14365. $120 squared. Miss Clark, those don't equal one another. Obviously, we're wrong. Not exactly. Remember, we've been rounding. So, if I were to actually plug this in, 120 sine 35 gives me that number, which I rounded to 69. And 120 cosine of theta 98, which I rounded down to 98. Okay, so if I actually took those actual numbers, I would get my 14400, which does equal the hypotenuse squared. So I'm right. The numbers are just slightly off because of my rounding. I could check it just doing this and know for sure, 100% of the time. But I'm never going to make you write out 68.829172236. That's ridiculous.
Can we also check it where you square and then you square this and when you round it, it can get to?
I don't know what this and that are. I don't know what you're.
Oh, okay. So like I did 69 squared plus 98 squared and I got me the 14,365. So when I square rooted, it was 119.85. So when I just rounded it,
Yeah,
do I still
absolutely.
get that?
Yes. Any questions? This is what we're doing today.